Well, good afternoon, everyone. Today, I would like to share with you, as I have slightly changed my topic, providing the feedstock gas for e-SAF rather than SAF. I made that small modification to my topic because feedstock is a big part of the cost of SAF. And right now, the difficulty with application of SAF is mainly at the cost. The society, the government giving subsidies are now making up for the extra cost of SAF compared to other fuel. But we want to make some breakthroughs there in terms of fundamental technology to address the problem of SAF cost. Our company is a spin-out from Hefei Industrial University, and since when we established, we wanted to reduce the cost of green hydrogen. That's why we brought forward SOEC-CH4. Technology. As long as you are in the electrolysis of water for hydrogen production, you know SOEC technology, solid oxide electrolyzer cell. But we added CH4 into it in order to reduce cost for green hydrogen. Originally, we wanted to provide a low-cost green hydrogen for hydrogen refilling stations in China. But at the time, we also have that zero-cost carbon dioxide. So we wanted to deal with that. So since last year, we started to focus on the market of SAF. With this facility, we offer low-cost hydrogen and zero-cost carbon dioxide emission, and the ratio between hydrogen and carbon is always 1:4. So it's perfectly suitable for SAF. Well, currently, the feedstock for SAF, like what we have discussed about in the morning, mainly those are the four mainstream process. HEFA was mainly discussed in the morning, though China had got 10 million tons of used cooking oils, but what can be collected is just around 3 to 4 million. Second process would be ATJ, and it has got certain risks because we have a competition with the food industry for the feedstock. The third process is the FT technology, Fisher and Tropsch. It requires the feedstock of agricultural waste, forest residue, and landfill gas, etc. And you'd have to generate a syngas from it and do synthesization with FT. But the problem is that the ratio between carbon monoxide and hydrogen is too high. So you'd have to add some extra hydrogen into it to adjust that mix of hydrogen and carbon monoxide. But FT technology is not that mature as people may have thought about, because you have those different contents inside, including aviation, kerosene, diesel, gasoline, etc. But if the feedstock varies, then the content would be different and the blend ratio would be different, and sometimes it wouldn't be economically viable. So we believe that in the future, in the longer term, the most viable way is the PTL. We use green electricity to electrolyze the water to generate green hydrogen, and then we capture carbon dioxide from air or from biomaterial or those carbon dioxide which the tax of carbon had already been paid. So basically with these different processes, they didn't solve the issue of power consumption in terms of water electrolysis. So that is the main challenge to PTL. And carbon dioxide capture from air, we know the concentration is very little, just 0.4%, less than 1%. And if you're in the ammonia industry, you know capturing oxygen with the 21% concentration in the air is already difficult enough. So carbon dioxide less than 1% is even harder to capture. But if we can actually solve that, then we can combine that captured carbon dioxide from air together with the electrolyzed water of the hydrogen from electrolysis of water in order to have this e-SAF. Now let's take a look at the current e-SAF roadmap. We have an electrolyzer here. We put in electricity there to generate oxygen and hydrogen, but within the electrolyzer, the oxygen has got no added value. But people have proposed that the oxygen produced from electrolysis can be used to do the gasification of biomass to generate biogas. If we can do that, then the biogasification can have its energy consumption reduced. But still, it doesn't solve the problem of electricity consumption for water electrolysis. That's why we put forward the SOEC electrolyzer. On the right side, you see we focus on bio-natural gas or biomethane. We combine those together so that within our electrolyzer, there are three inputs: green power, water, and bio-based natural gas. And the output are just two things: hydrogen and carbon dioxide. And then we can synthesize by combining hydrogen and carbon dioxide together to be e-SAF. So carbon capture, if being independent from water electrolysis, then both two sides are too expensive. But we have this electrochemical way of coupling the two together. Not just the hydrogen got much cheaper, the carbon is virtually free. And in June last year, we have launched this module, which is really small, 156 millimeter by 174 millimeter and 270 millimeter high. The energy conversion efficiency could reach 94.5%. And to produce 1 normal cubic meter of hydrogen consumes only 1 kilowatt hour of degree and consumes 1/4 cubic meter of CH4. At the same time, you can get a free cost carbon dioxide. The biggest advantage of this SOEC is to reduce power consumption of hydrogen production. And in our laboratory, as I said, 1 cubic meter of hydrogen production requires only 1 kilowatt hour of power consumption and 1/4 cubic meter of bio-natural gas, CH4. And the byproduct, carbon dioxide, is free of cost. So basically, you can make that calculation per kilowatt hour of green power. In China, it's just 0.25 yuan. Biogas, 1/4 cubic meter, that would be just 2 yuan, and you can calculate how cheap that 1 cubic meter of hydrogen would be. And basically, this is an electrochemical process based upon high temperature. The whole electrolyzer is using ceramic solid oxide, metal oxide, and it doesn't have that separator cost limitation nor the limitation from high cost of catalysts. So the capex in mass production would be pretty low. And when compared with traditional high temperature SOEC, once we introduce the biomethane, the working temperature can be reduced from 750 to 800 degrees to now just 550 to 600 degrees Celsius, so that all the stainless steel products and the equipments and the material cost would be lower.
And the second is the operation cost is lower for 1 cubic hydrogen. That is the with 1 kilowatt hours of electricity and the methanol. And also we can use the waste heat, and this can help to further reduce the energy consumption. And the hydrogen and the CO2 can be a syngas and produce SAF, and it also can do the coupling operation and reduce the energy consumption further. And another is that the whole installation is solid and it has no liquid state, and in which make it simpler to do the operation. So the operation is quite simple and economical. The whole reactor, its volume is 7.4 liters, and for every hour it can generate 4.5 cubic meters of hydrogen. If multiplied with 340 days, the SAF production for a whole year is 7.5 tons. And efficiency, and also looking at the scale, the efficiency is not correlated with the scale. It's different from the thermochemical. But for the electrochemical, the efficiency is not dependent on the scale, which means that the SOEC-CH4 can satisfy the smaller scale and the bigger scale cooperation. That means that it can work in the concentrated generation and distributed SAF production. So we can see this is with the input and the generate hydrogen and CO2, and no waste in this whole process. And looking at the scientific approach, so we see that normally when we have the hydrolysis and the hydrogen production, and we will have a 30 kilowatt hours and maybe with not so high efficiency theoretically, but with our operation we can do higher efficiency in the hydrogen production, and we also can produce the oxygen ions, and also it can be diffused to the anode, to the cathode. And also with the CH4, and it can be combined and generate water and the CO2. And for the anode, we can have the high concentration of the hydrogen, and we also can produce CO2 as at the cathode. And with the hydrogen and the CO2, we can do the SAF synchronization. In the traditional hydrolysis, we have no methanol produced, so this efficiency is lower. But now with this blue bar, that is the minimum demand of the electricity. But with the dotted green line, and that is to be compensated with heat, which means that the energy consumption is higher. And in the reaction, methanol and the oxygen, or the water and oxygen, so this is to release heat. So the heat can be compensated to the other generation. We have a membrane in between, and that is very thin, and the oxidation heat can be diffused to the cathode, and also the 60% of the heat can be supplied, and only the rest 20% will need to use electricity. So it means that the hydrolysis voltage is decreased from 1.3 volts to 0.3 volts. So if we calculate with the temperature and the heat generated, and that means for the future, the voltage, that is for every cubic meter of hydrogen, the power consumption is 0.6 kilowatt hours. So that is a very high energy efficiency. With the SOEC-CH4, what's the biggest value of the technology? So I believe that this can involve the waste of the husbandry, forestry, agriculture, and the industrial waste, and also the garbage, and also for the urban landscaping waste. And this can be converted into through the fermentation and to produce a biogas. And then the biogas, which contains 60% of the methane, can be used in the generation of the SOEC-CH4, and we can produce the hydrogen and the CO2, and then to generate SAF. And also with the water and the cracking, we can have the monoxide and the hydrogen, and can produce SAF as well. And the hydrogen and the monoxide can be synthesized and to build methanol, and this is an indirect way of producing SAF. And we also can have the CO2 with hydrogen. This is well studied home and abroad, and we can see the technology is as mature as the FT technology, and the efficiency is at the same level. And we also can do the CO2 plus hydrogen, and to produce the methanol, and then to produce SAF. So the technology can be very flexible and compactable to the different synthetic method to SAF. And it also can use diversified feedstocks and turn them into the high quality chemical products. And this is good for the circular economy. And also, when the SAF is consumed, it will generate CO2, and we also can do the capturing and the CCS, and also this can further reduce the waste, and we can have the closed loop of the circular economy. And this is what we have discussed in the morning. And I only want to mention the e-SAF part. In the EU, the commitment is 6% in 2030, and in the UK, that is 10%. And in this part, also there is a requirement on the e-SAF, that is to use other fuels than the UCO. So in the EU, in 2030, it should be 62%, and in 6%, and in 2040, it needs to be 10%, in 2050, 35%. And that means the current e-SAF cost is very high, and with the SOEC-CH4 technology, we can reduce the e-SAF cost, and this can also help with the widespread of the technology. In the UK, especially for the non-e-SAF, there is a penalty that is for each liter £5, and that is also a realistic cost issue. And our proposal is to have the SOEC and the CH4 technology to be coupled with the CO2 plus hydrogen technology. And if this coupling can be successful with one methanol and two H2O, we can have the 4 molecules of the hydrogen and 1 molecule of CO2, and we will have extra hydrogen. This is a high value added green hydrogen. If we want to have a SAF, we also need to add CO2 inside. So in the calculation, with 1 ton of a SAF, we will need 4,874 cubic meters green hydrogen. So you can see the price, and also the natural gas price, and the price of 1.5 kilowatt hours electricity. So in this calculation, and we also add on the capex and the FT technology. So in the whole calculation, we can see that the whole e-SAF operation for each ton, it will be €1,000. And we have not yet considered the coupling and the further cost reduction. And our system can run in 600 Celsius. And in the hydrolysis, it also needs the high temperature steam. And in the synthesizing of the SAF, it also needs 300 Celsius and 2 to 5 megaparts pressure, and which means that the energy we can recycle can be used in the electrolysis and produce the hydrogen. This is the energy coupling. And on the other hand, we also have the mass coupling. In the self-synthesizing, it is not 100% converted. So if we have the carbon 8 to carbon 16 and with the average of carbon 12, but it is inevitably we have the methanol and also the carbon 1, 2, and 3, and 4. So in this part, we can do the circulation, and this can replace the biogas, and we can better use the green carbon in this process, which is the mass circular loop. This is the price and the cost comparison. The traditional jet fuel, that is from the fossil fuel, and it has the CO2. So the trend is that it will be gradually replaced by SAF. The current pain point for SAF is a high cost. For the UCO, the cost of recycling the collection is for each ton $1,000, and the process is also €1,000, and that is quite high cost. And in the Euro's 2025 report, based on the current technology, it is estimated that on the right, if we can see the graph, the production of e-SAF 1 ton, that is 6,600 to 8,700 euro. If the CO2 is captured from the atmosphere, the cost is the highest, and the other route are simpler. But if we look at the other technology like the SOEC-CH4, the cost is only 900 to 1,200 euro. That is a much lower cost. And compare with the conventional jet fuel, if we can combine the waste collection and also the methanol generation and biogas generation, and also combine it with the e-SAF, we can do the e-SAF cost down and to make it competent compared with the conventional jet fuels. So with the SOEC-CH4, in the future, the e-SAF industry will be reshuffled, like the 3 kinds of waste and the methanol and the biogas production, and also it can involve the feedstock from the agriculture industry and also the urban, and the different producers can also involve in this industry. And also, we have been working with the CO2 and hydrogen producers, home and abroad. In the end of this year, we plan to have the demonstration project finished, and we will work with the producers and to do the pilot on the synthesizing, and we will have this implemented in the near future. And our company is Ceramic Cells, and we also will look at the technology partners from 2 sides. One is the equipment manufacturer, because if we want to make the electrolysis slot, we need the BOP equipment.
So we would like to cooperate with a system integrator to turn our devices into hydrogen production facilities. And secondly, we need technology integrators to put this device with everything in the upstream and downstream, so to do a feasibility verification. Okay, so a summarization of our technology It produces hydrogen with a low cost by leveraging the exothermic reaction and also produce free of a cost carbon dioxide byproduct and combining those together by using SOEC. Our technology comes from China Technology University, and the year before last, we got the 2 round of investment, and this year we are looking for a 3rd round of investment. So really, we would like to see any investors if they might be interested in participating in developing this technology. Well, we have established a little stand just outside of today's venue. If you are interested, you can come here and take a look at our stack. Thank you. Thank you very much.